My name is David Ostby, and I'm the Chief Science Officer for SavantX. I also have two SavantX employees here, Ed Heinbockel here, CEO, and Jacob Grummeyer, I think he's here somewhere. So, the title today is The Computable Human. It's kind of an intriguing title, so let's just jump right into it. So SavantX is a totally Mathematica version 10 written application. And for today, I think we're going to use the working definition of SavantX being a generalized relationship analysis system. Today I'm going to basically start with a big picture and then narrow down. We're going to take a slice out of SavantX because there's actually quite a bit to talk about. We usually do this in an hour, and we only have 20 minutes today. So, there's a brief history I could go into, and Ed was going to give that, but we X'd him out in interest of time. But basically, SavantX was, its predecessor was a product called DistroPro, and it ran on the cloud under Nimbus Systems, or Nimbus Services. And, and then we did a bunch of government work with that tool. It was called OSINT, or Open Source Intelligence. And then that eventually became SavantX. Okay. Our first client for SavantX looks like this. It's a power plant, a large power plant. It has 1,500 workers, 24/7, as you can imagine, providing electricity for 1 million homes. Lots of different job functions that you can imagine: financial, legal, accounting. Lots of information workers. That's why I have them represented by desks down there. Client issues. I can't find anything. I wish I could predict X, Y, Z, whatever. How do we fix this last time? Why did this happen? What's the relationship between X and Y? How would Harold have solved this? And then Harold retired. The truth is out there is that in the next 3 years they're going to be losing 80% of their workforce to retirement. So there's a big knowledge drain going on. Okay, to solve some of those problems, what do we have access to? One of the data sources we have is sensors. The plant has got, hundreds of sensors all over it. Temperature gauges and pressure gauges and things like that. And sensors are great because they have these characteristics here. You can see my little thing here. Homogeneous output's perhaps the most important thing. In other words, if it's a temperature gauge, it's always going to read temperature. It's not going to decide to read pressure or something like that. It has a known accuracy generally. It has known reliability. It works 24/7, kind of like Jacob does. Has continuous output. You can relocate the output somewhere, so you can have the sensor in one place, and then you can relocate the output to another place. It can endure in dangerous environments, and what does that say? Oh, it does have a fixed location. The thing is, you have all those sensors, but how do they really help you with the problem set that you have? Really not that much. Does it help you find anything? No, not really. Doesn't really predict anything. It might a little bit, perhaps, but not much. So go down through this list, you think, how do these sensors help? Now, it's true that there is a segment of the plant that's really interested in those gauges. And certainly the control room is. But that's a very small part of the plant, really. So, it doesn't really help that much. We have another huge data source, though. And that is the human-generated data. There are 1,500 people, as I said, and quite a few of them are information workers. They're producing about 1,000 pages of stuff per day, generally in the form of text. Some of it's structured, but most of it's text. Goes into databases. In this case, they have 35 databases. 50 million pages over time has accumulated. Almost all of it scanned because they got in the habit of taking PDFs of documents, which then would turn into scanned documents, and then filing it away in a document storage system. And so there it would sit. It's not really searchable. So what if we had a way of taking that text that's being generated and considering human beings as sensors of types? It sounds kind of like a crazy idea. The top of the list there, it's, you don't get homogeneous output from a human. They're uncalibrated, unknown reliability. They're slow to output. Can't really report from a dangerous location. And they output in a strange thing called human language. It's really non-computer comprehensible code. But on the other hand, humans are mobile. They can go anywhere in the plant. In fact, they do. They're swarming all over the plant. They're observant. They're smart. They can detect anomalies that a sensor probably never could do. They're already in place. There's lots of them out there. And they have existing reporting protocols. But if we were to consider human beings as sensors, what are they trying to tell us? So we need to figure that out if we're going to consider them as sensors. So if you look through our problem set that we had and kind of categorize the type of problem that it is, you come up with three general things, what we call search, discover, and analyze. So sometimes we say SavantX is a search, discover, and analyze tool. And you can see how they divide up here into this set. The first one, of course, is the one that brought us to the plant. Originally was they said, well, we just can't find what we're looking for. And it goes on from there. Prediction is, of course, an analysis task, and then how do we fix this last time, a search and discover task, and so on. So the first thing that Savant has to do is it wants to build a single place that everybody can go to get the answers to the questions they have. Why do we do that? Right now, if you have a problem at the plant, you have to figure out, which of the 35 places might the answer be? And then you have to go and run a specialized search tool or something within that database to find the problem, find what you're looking for. So at Savant, we have the saying, Savant's never met data it didn't like. So we have the ability to take pretty much any kind of file and turn it into text. That's eventually turned into indexes. And then, of course, the source document itself is retained in there. I'm going to skip by this. We don't have time. So now I'm going to go down into one particular aspect of Savant, namely search, and show you the kind of thinking that went into building Savant. And I'll go through these tabs and kind of describe how we do it. And you can apply that kind of thinking throughout Savant. Okay, so when we look at a search task, with the user, they have this vague idea that there's this bubble of stuff out there, and they might be trying to do a search for, say, a valve failure. And so they have this idea, I want this stuff to come out. It's represented by that bubble there. The thing is that this is really what they're getting. And that's primarily because almost all of these apps are using key term SQL kinds of queries to find the answers. We're going to describe to you why that bottom shape there is the shape it is. First thing that happens is that you have all this scanned stuff going on. If you don't turn the scanned stuff into text, there's no way you can search against it. And so that vertical line here, right here, is due to that aspect. Second thing is, we have what we call stemming. You really want to not only look for the word valve, but you want to work for the word valve or valves. And when you do that, you gain a little bit of some returns that you would not otherwise have. There is quite a bit of overlap, but not totally. And failure is even more interesting. This is actually taken from some of their data reduced down. So the proportions are probably correct. So failure is a pretty good word, but if you use the word fail, you would have only gotten this. But by doing stemming, or the roots of failure, you find all of this information here, like that. So it increases your return set. So by stemming, you basically can doing some Boolean type logic on that. You'll get that long list of possible variations on the search terms that the user typed in. I don't know if you can read those, they're pretty small. Maybe I can make this a little bigger here. See if I can do this. Let me do it easily. There we go. Let's try that. Okay, so that's gotten us to where we have all these returns now. But the problem now is that you have a lot of stuff, and I'd say generally about half of it's useless. Now, why is that? One of the reasons is that at the plant, they have a lot of documents that are hundreds of pages, thousands of pages. In fact, we've seen a couple that are over 10,000 pages long. And that means that basically those documents have every possible term in the plant in them. So pretty much no matter which kind of search terms you type in, you're going to get those documents returned to you. It's not very useful. So we really want to find out context. Now context, the traditional kind of weapon of choice has been LSA, latent semantic analysis. And that's a technique that was invented by Bell Labs back in the 60s. It's pretty interesting, mathematically speaking. What they would do is they would take a passage of some text, say like this, and then that would go across the top, and then down the left-hand side they'd put the vocabulary found in that passage, and they'd put the number of hits they would get for that passage in this matrix. So that matrix gets very large, as you can imagine. If you have millions of documents, you're going to generate probably hundreds of thousands of terms down the left-hand side. And it's a sparse array. It's mostly filled with zeros. But then if you do a singular value decomposition on it, you can turn that array into 3 arrays, such that when you multiply them together, you get the original matrix back. And the center array is the singular values, and the left-hand side and the right-hand side are at right angles to each other. The net effect of it is that you can then squeeze the array, kind of squeeze the noise out of it, squeeze it way down, and turns out through a pretty interesting trick, you actually get meaning from that. You can actually extract meaning from passages. The problem is, with LSA, is it requires a supercomputer to decompose these arrays. And then when you add yet another passage, just one more passage, you get to do the whole decomposition again. Because to find out how that passage relates to the other passages, you have to take the vector and reduce it down, and it's a big job. I have a little example here of how LSA would work against a photograph, if you decompose a photograph. So I have a photograph here that's 512 pixels by 512 pixels square, and I've now reduced it down, the singular value decomposition, down to 1 dimension, and this is what the picture would look like. And as you add dimensions back in, you'll start to see something. We're at 3 dimensions. Probably some of you know what this is already. So we get to 5, 6, 7, 8. Start to see a face and so on. So out of those 512 dimensions, at say between 8 and 12 dimensions, you're going to start to see concepts of sorts. Now, so that's how LSA works. But if you don't have a supercomputer, you can't do that. So, and our client certainly doesn't have one of those. The only people that really do that kind of work is maybe some basic work at Google. They might do some peer research there, and the government's done some work with this too. But certainly not your average company. So we had to come up with a different way of computing context and meaning at Savant. So what we did is I'd done some work with previously with networks, and which is based on graph theory. And so I decided to look at text. Let's say we have some text down the left-hand column here, and then form relationships between them as though there are nodes on graphs. It looks like this. I drove my car into work today. I can make these relationships between drove and car and work and today. I paid insurance on my car today and so on, so you get these relationships. So you might say this is the 1D version of that right here. If we look at that in 2D with graphing theory, you get this. Obviously, car is a central theme of that set of text. And then you have these relationships here going out. And we can look at it in 3 dimensions like this. All pretty standard Mathematica stuff. I have another set of text. Let's say it's about an airplane. I always wanted to fly, or to learn how to fly an airplane. You get this relationship here. I fly my airplane to work every week. You get these sets of relationships and so on. If you look at that in 2 dimensions, you get this, as you would expect. If you look at it in 3 dimensions, you see it this way. But what happens when you combine both of them together? If you look at it in 1 dimension, you see this. It's not actually very easy to tell what that's trying to tell you. If you look at it in 2 dimensions, it looks like this. This is a little more interesting. First of all, you see that airplane and car are centrally located. They have no direct relationship to each other, but they have all these things that they share around the periphery. If you look at it in 3 dimensions, it's pretty interesting. Notice that no matter where I twist this, car and airplane are never far from each other. The reasoning for that is pretty much the same reason why LSA works, which is when words share relationships, they form a context with each other. And so even although you use different terms, if they're sharing other words, they probably share a meaning. In this case, it's transportation. And so I can twist this around. Notice that the words that are in the periphery are less related than the ones that are closer in. And for instance, drove and fly are out by themselves because that's one of the ways they're differentiated from each other. Okay, so now how about a real world example? Unfortunately, I can't really show you the terms that are involved in this, but this is the word ladder, looking at some plant data and doing that same kind of computation. You'll see the word ladder is actually centrally located here. They're not labeled, but it's in the center. These dots that are out here, these nodes out here, are other words which are less related, and then more centrally located terms are more related to the word ladder. So we could look at that in 3 dimensions, like this, and you'll see some very nice clumping that's going on. It's kind of like words make a social network of sorts, and some words like to hang out together more than other words. And so you get this clustering effect. And so as you increase the dimensionality of your analysis, you'll get better and better clustering. The thing is, after dimension 3, the human mind can't understand it. There's no way for us to display above 3 dimensions, but Savant can actually think up into 5, 6, 7, 8 dimensions, not unlike what we saw, that mathematical intuition on the LSA graph that I showed you in the photograph there. So when you type a word, say ladder accident, into Savant, it actually thinks about ladder this way, and it thinks about accident, something like this. And then it looks at the relationships and can tell which concepts are centrally located to those, and then do an index into those documents that have that feature. Okay, I got to go quick here, kind of run out of time. So let's go back to our original problem here. Here's what they wanted, and here's what they got. And so I'm going to explain here real rapidly how we how Savant actually gets this correct bubble. First of all, it gets this half of this bubble here because we actually turn the scan images into text with OCR. These here, this little segment here that we don't want, is eliminated by our LSA replacement of graph theory. This section in here is handled by stems. And this piece up here is from some Savant AI that we don't have time to talk about today.